Hello everybody. Welcome to the Studium Generale. We're getting closer to the summer, so it's also the end of the cycle of Studium Generale talks, but I think you're lucky to have a very nice talk about a very remarkable scientist who passed away, unfortunately, beginning of this year, not so long ago, Stephen Hawking. Very happy you're here. Tonight we will have, my name is Joost Adema. I work with the Kaptein Institute. It's the astronomy department of the university. I myself am not an astronomer, but I build instrumentation for telescopes and satellites at our institute. So I'm not a deep theoretical person as these two speakers. It will be two presentations. First by Erik Bergshoeff from the University of Groningen, and he will talk about the impact and the influence that Stephen Hawking had. And then later there will be Daniel Baumann from Amsterdam, who will go more into the real work of Stephen Hawking, especially focus on his three major scientific achievements. So I would like to give the floor first to Erik for his presentation.
Yep, this works.
Okay, good evening everybody. It's a great pleasure for me that I can say shortly something about Stephen Hawking as an inspirer. I mean, what made it really that Stephen Hawking was such an inspiring figure for people both inside my field of physics but also outside physics. And when Hawking died 2 months ago in March, obviously many people were interviewed, and often the first questions were, how did you meet Hawking? What were your personal encounters with Hawking? What do you think about Hawking? And that led even at the on the Dutch television in the Wereld Draait Door program to a funny performance by the comic duo The Partisanen, where one partisan interviewed the other one, and he claimed that he had met Hawking already under the name of Steen Habbing at the Peuterspeelzaal in Tinalo and the kindergarten, and he was even kind of annoyed with Hawking because he claimed that one day he had told Hawking, why don't you have a look at this beginning of the universe and the fatal black holes, and it was originally coming from him. And there's a kind of funny video which I can recommend you to watch on the internet. It's unfortunately only in Dutch, so you have to understand Dutch, but it's kind of funny. But I thought it's indeed nice to also start my presentation with how did I met Hawking for the first time, and a few reminiscences before I start talking about Hawking as an inspirer. So I met Hawking for the first time in 1985. I was then a young postdoc at the ISTP in Trieste, and this was my first big workshop to go to in Cambridge. And I remember we went with the night boat from Holland to Cambridge, and there was then a workshop on the then new research fields of supersymmetry and supergravity, and that was organized by Hawking and by my then collaborator Paul Townsend, and then by Gary Gibbons, which was a more senior collaborator of Hawking. And so you see already Hawking was not afraid of new ideas. These were really new developments, superstrings and supergravity, but he was not afraid for that, and he vividly participated in organizing workshops in that field. And it was a very nice workshop, my first workshop, and I remember also one day there was a reception at the home of Stephen Hawking, and then there was a reception in the back garden, and then everybody was walking around, and there was also the wife of Stephen Hawking, his first wife, and how their marriage developed, you can see in the movie The Theory of Everything, 2014. They didn't unfortunately stay together. He later remarried one of his nurses. But then it was a happily married couple. It was really nice to have this reception. And in those days there were also people of my age, like I remember postdocs and PhD students like Nick Warner, Chris Pope and Chris Hull, and they really could communicate directly to Hawking. So here you see Chris Hull, he is in a very young stage, he's now my age, and you see Hawking here, and they really they discuss, there's a direct communication possible, and we were discussing then these supersymmetry and supergravity, and you can really recognize, well, at least I can recognize some of the formulae on the blackboard. You also see that how primitive the wheelchair of Hawking was. This was really a kind of almost shabby wheelchair with, I think, some Hematasche at the end, and so they talked, and that was the way it went. Now, the next time I met Hawking was in 1997, because then the people from Amsterdam, Utrecht and Leiden, no, sorry, and Groningen, Leiden was not involved, we managed to get the yearly string conference, which was always organized in the United States, for the first time to get it to Europe, to Amsterdam. And this is the poster of that Strings 97 conference made by Robert Dijkgraaf. And so the whole week there were seminars, and then the Saturday after that week there was a special symposium where some people would give popular talks, and one of the people who was invited was Stephen Hawking, and that was done, I remember, in the Koepelzaal of the Amsterdam Renaissance Hotel. And this picture is made on that day, and I think it must be somehow during lunchtime, and so here you see Hawking, we're outside. You see also very young Robert Dijkgraaf with his wife, and you see many people with a white tag, because these were the conference participants. They could freely participate to the symposium. And here in the middle you see Vladimir Kaplinowski, a physicist from Austin, Texas. He was our most oversized colleague we knew, and we always had to arrange a special chair in the first row to position him. But so that was the first time that Hawking came to the Netherlands. Then the next time I met him, that was in 2011, because then my collaborator Paul Townsend, which I earlier mentioned, he became 60 years old. And in our field, it's then a tradition that you organize a special conference for such a person, which was done, but also somehow there was the idea to organize a surprise party, and it was my task to seduce Paul Townsend to a restaurant in Cambridge, where then the whole group of Hawking, because he was part of the Hawking group, or at least the people who he knows best, and some other friends of Paul Townsend were sitting there, and then there was this surprise dinner. So here you see me entering the restaurant, and because he was gone to the restroom, and so here you see the whole group of people sitting. This is the nurse, the then nurse of Hawking, and I'm saying he's arriving soon, so be ready. And then he was here, he came, entering, and then we had a nice dinner together with all of us, and Hawking was also there, and this was his nurse, and we were all sitting there with people like David Tong, I remember Malcolm Perry and Kelly Stell. So it was a nice evening. But I must say that Hawking is there, but you cannot communicate. So it's not that you say, like, hi Steve, did you like the food tonight? You more somehow talk to the nurse, and I'm sure he noticed everything, and he enjoyed the evening, but somehow well, it's difficult to communicate, and if you ask something, you get an answer much later. So he was a bit isolated also, I must say, from the room. Now, the last time I met him, that was in 2015, and I was then visiting Leuven University for a PhD defense, and Hawking was also then visiting Leuven, not because of one of his popular talks, because then thousands of people would come, but just he was there for a working visit, because he worked at the time with Thomas Hertog, with whom he wrote his last paper, which appeared after his death, and James Hartle was there too, and somehow the Belgian television had gotten an idea that we were there with a few people, is to organize a special Hawking dinner in the faculty room. So that the idea was that it was a nice round table, and we would sit there with something like 6 or 7 people, including Hawking, and there was a woman from the Belgian television, and then she would interview Hawking, and it would be a very nice dinner. And there was even a special menu card. You see, it was really nice. It started with carpaccio of organic salmon, followed by lamb cooked medium rare, followed up by a small chocolate brownie, and finishing off with coffee and dessert. So you can imagine we were really ready for this nice dinner. But it was in the summer of 2015, it was very warm, and just half an hour before we would go with dinner, we heard from the nurses of Hawking, was still in his hotel, that he didn't feel good, so that the whole dinner was cancelled. The woman from the Belgian television went home, and all this you see in the menu card we didn't eat. And in fact, what is funny is that the next day he felt better, and he came to the department just to work with Thomas Hertog and James Hartle, and then in the lunchtime we were sitting in the coffee room, and then we eat together, but that was of a different nature. So it was literally an afhaal Chinees, as they say in Dutch. And the exquisite wine, which I would have expected, was this can of water. And you see Hawking, now he has 2 nurses. You also see the wheelchair has become more complicated now with this television screen. And here you see Thomas Hertog, also in an informal setting with short pants, the guy from Leuven who worked with Hawking. So these are my encounters. Now you might say, wait a moment, Mr. Bergshoeff, you mentioned a reception in a garden, you mentioned a surprise dinner, you mentioned a nice dinner, you mentioned an afwaalchinees. Are your relations with Hawking only of a culinary nature? I mean, there are also scientific interactions, but I must say yes, because what is funny, I remember this Hertog and Hawking, they published this paper after he died. So just a month ago, they published it. That was in April 2007. And it is about the beginning of the universe. I mean, maybe Daniel will say more about it. But it's funny that they do refer to a work I did 10 years earlier with 2 students here in Groningen, Jelle Hartong and André Ploeg, and 2 students from Leuven, Jan Rossel and Dieter van der Bleken. And it's called Pseudo-Supersymmetry and a Tale of Alternate Realities. And it was somehow needed for this work. The word alternate realities, that is 10 years earlier, it looks a bit like the alternative facts of Trump. But I can assure you, this has nothing to do with Trump, which was then not in the picture. But he did use our work in his 10 years earlier in his very last paper. So there was also a scientific interaction. Anyhow, having talked now about all these encounters, let me also try to ask the question, what made Stephen Hawking now so special? Why is he so inspiring and not one of our other colleagues? And if you think about that, then it's also of interest to think about other icons in physics, and 2 of them come to my mind. That's Newton and Einstein. Now, Einstein, I think we all know, because that was the inventor of the modern theory of gravity, general relativity. I don't dare to ask the question who don't know Einstein. Newton, I'm not so sure. He's a few hundred years older, and most of them from high school knew him from the 3 laws of Newton. But is anybody who dares to say now, I don't know who Newton is? Could you pick up your finger? And is there somebody who had never heard of Newton? Let's say the man of the street. Well, are there many men of the street here? But everybody knows Newton. Okay, that's good. It's quite good. But I wish to compare a bit with Einstein, because I think Einstein still is really known also to the man on the street. So the idea is that really, why was Hawking so important? Well, first of all, one reason is really the science. If you don't do good science, then nobody will listen to you. And Hawking did, that will be mentioned by Daniel, did work in the world created by Einstein about gravity, and he investigated their confusing issues like the beginning of our universe and the fate of black holes. And he did their important contributions, and black holes is something which will get more and more in the intention of research, so I'm sure this work of Hawking will be relevant also in the coming 10 years. So that is one thing for all. He did excellent science. Then it's really a combination of factors. Then we all know, of course, he had this disease. It is the man in the wheelchair. You see, the wheelchair in the course of years has become more and more fancy. This is one of the latest versions. And we know he had this ALS disease, this amyotrophic lateral sclerosis, also known as motor neuron disease. And I'm not a doctor, but it has to do with that your muscles are not good steered and they get weaker and weaker. But because he got it in the early age, development went very slowly. So he still became reasonably old. And also the good news is also that his brains were not affected. So his brains were in top condition. And that's very important because I know some of my colleagues, unfortunately, they were hit by a stroke and they recovered. They came back to the institute, they started giving lectures, administration, but they never did research anymore because after all, don't forget, research is top sport. So your brains really have to be in top condition. If they are just a little weaker, you can't do research. So, and he was able, clearly his brains were in top condition. He kept doing research for really the rest of his life. So you see, he looks helpless, but don't underestimate what is in the brains. It was just working. It was only his muscles which were not working. Then another thing I think which helped is also that he was a good popularizator. He wrote some very famous popular books. I think the most well-known one is the one from 1993, A Brief History of Time. And I've spoken to many young people, physicists, and asked them, how did you got to do theoretical physics? And many of them answered, well, when I was young, I read this book by Steve Hawking, and I got interested in it, and I wanted to do theoretical physics. And you really see here also the statement that this book marries a child's wonder to a genius intellect. The journey into Hawking's universe while marveling at his mind. So he kept the wonders of a child. And that brings me also to the last point, and I think that's also, don't underestimate that Hawking also had a good sense of humor. He was what we call in Dutch a bit studenticos. Now I tried to look it up in the Google translator, but I can't find a word of they say student-like, but that's not nice. Studenticos means a bit playing with the laws, conventions, and do funny things, and that's what he did. I mean, for instance, he figured in the television series, The Theory of the Big Bang. He figured in The Simpsons. At some point, he let people know that he wanted to feel how it is to be weightless, so they brought him in a special airplane where you see him having fun. And even in a recent interview, he said that one of his dreams was to ever figure also in a James Bond movie and to play the Bond's villain. But unfortunately, it never came to that. But I think that is also very important, that is humor. That is also really what people not particularly relate to physics like. And these four things together, that make him really such an influential and inspiring figure. If you compare it with Einstein, then part of it Einstein had too. Of course, Einstein had an excellent scientific achievement. He invented the modern theory of gravity, that space was important to show how gravity works. Space can change in shape and can get deformed. And Einstein also was known for his humor. This is his tongue taken out to photographers who want to make a picture of him while he was riding away in a car. And so that is nice. Of course, Einstein he was not disabled, and he's also not known really for popular books. But on the other hand, what Einstein had was that it was a political issue, that when his theory was confirmed, that was in 1919, that was 1 year after the First World War, and it was confirmed by the famous expedition of Eddington, an Englishman. So there was first the World War, where Germany and England were enemies, millions of people died, and people were sick of it. And what was nice now to have a new start where a German, Einstein, invented a new theory which was confirmed by an Englishman, by an expedition led by an Englishman. That was really the beginning, 1919, the fame of Einstein. And the other thing is also Einstein is really known for his quotes. I don't know many quotes by Hawking, so you could say Einstein is really the Johan Cruyff of physics. So like we all sometimes say, every disadvantage has an advantage. So Einstein is also known for many quotes. Although I must say, if you look on the internet, also many quotes which are not by Einstein, but people say they are by Einstein, but they are not. But Einstein is also known by a quote. But again, it's a combination of things. Good physics and a few other things. That is really what makes it very special. There are many people who have one of these properties. They are good scientists, or they write, for instance, very popular books like Brian Greene, but they don't have all the different things together. And that really explains why Einstein is so inspiring. So, and if you ask me, is he also inspiring for people outside physics? Well, a proof of it you have here. So I just came back today from a sabbatical stay at the Perimeter Institute in Waterloo in Canada. And when I was there for 2 months, and one night I went out for dinner to an Indian restaurant. And then when I left the restaurant, I saw this picture where, because Hawking, he also had visited the Perimeter Institute, and he's fond on spicy food. So he also had dinner there, and then he was photographed together with the owners of the restaurant. And clearly these owners, they are owners of an Indian restaurant. They're not physicists, but look how happy they look. This man, his smile goes from ear to ear. They are really extremely happy just because Hawking had dinner in his restaurant. And I think that is really the proof that Hawking was really an inspiring figure for many people, not only in academia, but also beyond academia. And that is really very special. And I think that is a nice end also of this short presentation.
Erik, thank you very much. Later, there will be more opportunities for questions if you have them. For now, we continue, or prepare to continue, with Daniel's presentation, more on the science of Stephen Hawking and his achievements. And then connecting is always an issue.
Oh, yeah.
Now it's working.
Okay.
So I give the floor to Daniel.
All right. Thank you very much. Actually, so this is not yet my talk. This is just your poll about Newton reminded me of this poll that was done in the U.S., where people in the U.S. were asked, can you name a living scientist? And 81% cannot. This was before Hawking died, so in principle. So then, but when you look at, the first shocking thing is that only 19% of the population can actually name a living scientist. Of those 19% is then 27% who name Stephen Hawking as the scientist that they know. And then you can see the rest, 2%, name themselves. But it's well, maybe as an appendix to Eric's talk, it just shows you how much, it shows you something about the US and something about the influence that Stephen Hawking had in the public. Okay? Yeah, so thank you very much for inviting me. It's a real pleasure to be here. It's an special honor for me actually to talk about Stephen Hawking, who definitely was one of my scientific heroes. And so it's really a privilege for me to actually describe his science to you. So I had a lot of fun preparing this talk, so I hope you enjoy listening. So the organizers also asked me to say a few words, like Eric did, about my personal connections to Stephen Hawking. And so I want to do this quickly so that we can talk about the science, but I will say a few words. So my interactions, quote unquote, with Stephen Hawking started in 1993 when I was at high school. And so I was one of the people reading his book. In fact, it was the very first book on science that I read. And I have to admit, I understood almost nothing of this book, very little. But I found it fascinating. I still, I made it through the entire book. I was hearing words like imaginary time and no boundary and very fancy stuff. And I wanted to learn what type of physics this is. At that time, I actually hadn't studied physics at all. So I decided to study physics. In fact, I went to Cambridge as an undergrad student in 1999. That's when I started there. I was a groupie at one of the talks that Stephen Hawking gave there. So that's Stephen. This is Roger Penrose from the back. So Stephen Hawking and Roger Penrose, did some famous work together that I might mention. So I was okay, but at Cambridge, actually, I didn't have that much interactions with Hawking. I ran into him from time to time on the street, but that's about it. And also, my undergrad degree, in fact, didn't give me enough education to actually understand what he was talking about. So still, the kind of science I will be describing to you tonight is very high-level theoretical physics, and an undergraduate degree in physics will not be enough to understand it. So that's meant I had to study further, so I did a PhD. So I did a PhD in the US, and finally in 2006, so 13 years after I read his book, I could understand a fraction of what he was talking about. In particular, I could read one of his famous papers. This is one of the things that we're going to be talking about later. So I did my PhD. I finished my PhD in 2008, I believe. And then 2 years later, I got a letter from Stephen Hawking, and I was offered a job in Cambridge. So I went back to Cambridge in 2010 to be a colleague of Stephen Hawking for 5 years. So this is one of our seminars. In fact, it's actually a very famous seminar where the bicep result was announced. So Stephen and I were very happy and then very disappointed months later. So I really had the privilege for 5 years to be working very close to Stephen. In fact, sometimes I'm joking. I mean, I was very close. In fact, my office was the one next to his, separated by a toilet. So he had a very big office, then there was a toilet, and then there was my office. So, okay, so this is everything I wanted to say. I'm mostly here today to talk about the science of Stephen Hawking. And so I separated this talk into 3 parts, and we will see how far we get. So I want to first talk about Stephen Hawking's work on black holes, and that's going to be the main part of my talk. I'm then going to be talking about the Big Bang and what Stephen has taught us about the origin of the universe. And then, if there's time left, I will say a few words about speculations that Stephen has had on really the origin of time itself, how everything began. Okay? All right, so I want to start with black holes. So let me just remind you what black holes are. So black holes are one of the most fascinating and mysterious objects in the universe. Okay? They're also very simple objects. So you get a black hole when you study Einstein's equations of gravity. In fact, the very first solution that people found, called Schwarzschild, just a year after Einstein introduced his equations, found this solution to the equations that describe the black hole. Okay? It's actually a very simple solution to the equation, but people for a very long time wondered whether this solution is real, whether it can arise in nature. So they didn't doubt the mathematics, but they doubted whether this can ever happen in nature, that something can be compressed to such high density that the gravity on the surface of the objects becomes so large that nothing, not even light, can escape. That's what a black hole is. And so even Einstein, for a very long period, didn't believe that black holes really existed. And it took until the 1960s or so, people made more and more convincing theoretical arguments that when you have a very massive star and that massive star runs out of fuel, it has to collapse under its own gravity and nothing will stop it. And it will collapse to such high density that it will form a black hole. Okay? But that was still theoretical. That's what we thought would happen when a star runs out of fuel. And then it took more time to get experimental, observational handles and evidence that black holes really existed. And in fact, the most spectacular evidence and really proof that black holes exist came a few years ago. Okay? This was an amazing event, amazing event. What we saw is that two black holes were colliding. The gravitational effects of that collisions were so extreme that they created ripples in space. Those ripples in space propagated through the universe and then were detected by the LIGO experiment. Okay? And you can calculate exactly, according to Einstein's equations, how this should look, and it looked exactly how two black holes merging will look. Okay? So very few people that are not crackpots do not believe that black holes are real. Okay? Okay, so these objects exist in nature. Nevertheless, they're still mysterious. From a theory point of view, they're still one of the mysterious objects in the universe. And a lot of the mystery of black holes was either solved or initiated by Stephen Hawking. And so I want to describe some of these mysterious aspects. And so in particular, I want to describe two puzzles of black holes. The first one is called the entropy problem, and the second one is called the information paradox. Okay? So let me describe first the entropy problem. And so to describe the entropy problem, I have to tell you what entropy is. Okay? So when a physicist looks at a cup of coffee like this one, we like to reduce the cup of coffee to a couple of numbers. So numbers like the temperature of the coffee, the pressure, the energy. Okay? Those are things you probably know. A quantity that also is very important that you might not know is called entropy, which measures the amount of disorder of this cup of coffee. And disorder means basically it's counting the number of ways that you can rearrange the parts of a system and leave the system looking the same. Okay? So if you have a system that's made out of many parts and you scramble the different parts of the system and it still looks the same, that's an object that has very high entropy. Something that's very ordered, if I change it a little bit, it will look different. That has low entropy. Okay? That's all the physics you need to know. The other important thing I need to tell you, though, is that there's an important law of nature. It's one of the strictest laws of nature that we should not be violating, which is the fact that the entropy of the universe always increases. Okay? So what does this mean? Imagine I take this cup of coffee and I pour some milk in it. Okay? What you have is you have a layer of milk and you have the coffee. So when I now rearrange the molecules inside of the milk, I can't do that too many ways because otherwise I would be mixing the milk. So that's a very low entropy configuration. But if I actually start mixing the coffee, I will mix the milk and the coffee. It becomes one entity. And now I can rearrange the parts in a lot of different ways and it will look the same. But that's a high entropy object. So things always flow from low entropy to high entropy. Coffee and milk will always mix, but I can't unmix it. If I keep stirring it, it will not go back to milk and coffee separated. Okay? So that's the law. It's called the second law of thermodynamics, or just the second law. If you tell a physicist the second law, they will all know what you're talking about. Okay, so what does this have to do with black holes? So apparently one day in 1972, John Wheeler, the famous physicist, talked to his then graduate student Jacob Bekenstein. And so he asked Jacob, what happens when you take a cup of coffee and you throw it into a black hole? Okay? So what Wheeler thought is if you throw a cup of coffee into a black hole, this cup of coffee and the entropy associated with that cup of coffee should be lost from the universe because nothing can escape. Okay? It looks like a situation where you can actually decrease the total amount of entropy or disorder of the universe because you just completely remove this cup of coffee. Okay? But that would be a violation of the second law of thermodynamics, which people really don't like. Okay? And Bekenstein in particular didn't like it and said this can't be true. Okay? And the only way to save the second law is to postulate that the black hole itself has to have an entropy. It has to carry some kind of disorder that compensates for the fact that I lost something. This cup of coffee. And so Hawking apparently was very angry about this. Okay? He thought this was ridiculous to say that a black hole has entropy. Because something that has entropy in thermodynamics also has to have temperature. And something that has temperature has to radiate. Just like our bodies. I'm radiating infrared radiation because I have heat inside my body. So he thought this was logically impossible. If something has entropy, it has to have temperature. If something has temperature, it has to radiate. But a black hole is black. It doesn't radiate. Ergo, it can't have entropy. Okay? So that's what Hawking was thinking in 1972. Okay, but then after a little bit of more reflection, Hawking started thinking about empty space. Okay? And Hawking knew that in quantum mechanics, actually, empty space isn't really empty. There's no such thing in quantum mechanics as empty space. Because if you take space and you take everything out of space, you thought you made it empty, that violates the uncertainty principle of quantum mechanics. Yeah? The statement that you can't have a state that is perfectly well defined. Okay? Things have to be fluctuating. And so in particular, what it means is that even in empty space, there can be spontaneous creation of particle pairs with positive and negative energy for a short amount of time. And so physicists often call these virtual particles. Okay? So usually this is a small effect. So this happens here in my hand, if you look closely. There's particles, antiparticles being created and annihilating. Okay? But it's a small effect. We can actually measure it when we look very carefully at the atomic structure of hydrogen atoms and so on. But it's a small effect, not affecting our daily lives very much. Okay? So Hawking was asking what happens when this effect occurs close to a black hole. Okay? So these particle pairs are created in empty space. But if you're very close to a black hole, it can happen that one of the members of this pair falls into the black hole, and then the second one has lost its partner to kill, to annihilate itself. So this second partner will then become a real particle. Okay? And it will look from the outside as if the black hole is giving off radiation. Yeah? Just because of these virtual particles are being created, one of them escapes, one of them falls into the black hole. The one that escapes looks like a radiation. And so that effect is called Hawking radiation. Okay? So Hawking discovered by this way a mechanism by which if you take quantum mechanics into account, black holes are not really black, but they can radiate these particles because of this effect. Okay? So that's probably his most important discovery. It's called Hawking radiation. So it's fun to put in some numbers, in fact, to ask, how big is this effect for ordinary black holes? So for example, the black holes that we discussed, from the LIGO experiment, these black holes have masses of around the sun. Yeah? So this M sun means this is the mass of the sun. So and this is the mass of the black hole. If I plug this mass in, I get a temperature which is 10 to the minus 7 degrees Kelvin. So it's 10 to the minus 7 degrees of something above absolute zero. It's a tiny, tiny temperature. Okay? In fact, this temperature is smaller than the temperature of the radiation that fills the entire universe, the cosmic microwave background that I'll talk about later. Okay? So this is one of the lowest temperatures possible in the universe, and so it's a very tiny, tiny effect. But you also see that this effect scales inversely with the mass of the black hole. So this is the mass of the black hole. So smaller black holes actually will radiate more quickly and emit higher temperature radiation. So for example, I did this estimate yesterday. If you took the entire mass of the Earth and collapsed it into a black hole, you will get a temperature, this black hole will radiate, and will radiate with a temperature of 0.1 degrees Kelvin. Okay? Still quite low. If you then divide up the Earth and just take the Netherlands, okay, and you compress the Netherlands into a black hole, you actually get 10,000 degrees. Yeah? So it's a black hole radiating with a temperature of 10,000 degrees, which is about the temperature of the sun. But this kind of black hole, you shouldn't even really be calling a black hole because it doesn't look black. It looks white light, like the sun. Okay, so that's what you would get if you take the Netherlands and make it a black hole. All right. So because this black hole is emitting radiation, it's also losing energy. Okay, and so you can ask, how long does it take for the entire black hole to disappear? And so this is what it is. Again, if I take the mass of the black hole to be the mass of the sun, roughly, you will get that it takes about 10 to the 67 years for this entire black hole to disappear. And the age of the universe is 10 to the 10 years. Okay? So this is much, much, much longer than the age of the universe. Okay? So for practical purposes, for ordinary black hole, this is not a very important effect. Yeah? In fact, usually there will be more stuff falling into the black hole randomly than this heat that's given off by the black hole. Okay? So the black hole will actually not shrink in practice. But it's very important for theoretical reasons. Okay? And the reason it's important for theoretical reasons is because now that black holes have temperature, it also means that they can now have entropy. And this argument by Bekenstein that black holes have entropy and therefore save the second law of thermodynamics has some microscopic validation. Okay? So, and Hawking finally accepted that, okay, black holes do have entropy, and I know why. Okay? Because they're radiating this Hawking radiation. So I thought I should give you one formula. Every great physicist has their personal formula. So Einstein has something like E equals mc squared, and Newton has this gravitation law, or F equals ma. And so Hawking has this one. Okay? So this is really very quantitatively calculating this effect and calculating the entropy of a black hole and showing how it depends on the area of the black hole and some fundamental constants. Okay? So it's a proportionality between entropy and area and some constants. And these constants are fundamental constants of nature. So for example, this constant k here is called Boltzmann's constant. It's what turns a temperature into an energy in thermodynamics, for example. Here, this variable c is the speed of light of relativity. This h is Planck's constant of quantum mechanics. This g is Newton's constant. Okay? So it's a beautiful formula because these constants here are basically all of the fundamental laws of nature that we have. Thermodynamics, quantum mechanics, relativity, and gravity. Somehow all are combined in this law of black holes. That the entropy of a black hole is proportional to the area with these constants. All right? In fact, one can write this formula even in a slightly nicer form. You can absorb the Boltzmann constant just in the entropy and make entropy just a number that counts the number of ways I can rearrange the parts of the black hole on the surface. And the remaining constants can all be combined into a length scale. And so this is called the Planck length. It's a very small length scale. It's 10 to the minus 35 meters. Tiny, tiny. This is 20 orders of magnitude smaller than an atomic nucleus. Okay? So it's a tiny length scale. It's the length scale at which quantum mechanics and gravity become equally important. So if I look with a microscope on very short distances, at those distances I will see very violent fluctuations of the space-time because of quantum mechanics, and gravity will also be important. So for some reason, the entropy of a black hole counts the number of times I can fit this fundamental quantum gravity scale onto the surface of a black hole. Yeah? If I divide the area by this fundamental unit of area, I get the entropy. Okay? And this is typically an enormously large number because this is tiny and black holes are still big, although they're highly compressed. But for example, the black holes that LIGO has seen have a size of about 1 kilometer. And so that area relative to this area is still enormous. And so you'll get very, very large entropy. So any successful theory that combines quantum mechanics and relativity and gravity and quantum mechanics, something that we don't have yet, needs to explain this formula. Yeah? It needs to explain why it is that this fundamental constant appears. It needs to explain this factor of 4. And it also needs to explain why the entropy scales with area and not volume. Okay? Actually, this is something we otherwise have never seen in nature. If I take this cup of coffee, for example, and I take a second cup of coffee, I will double the entropy. And so entropy will just scale as volume. Yeah? The bigger I make the volume, the more disorder of the system I have, always proportional to the volume and not the area. Okay? Somehow for black holes, that's different. Okay? Black holes, somehow the amount of disorder that a black hole carries is not determined by the volume of the black hole, but just by the surface area. Okay? And people don't completely understand why. All right? Okay? So this was the information problem. It arose because Bekenstein was throwing a cup of coffee into a black hole. And then Hawking solved the entropy problem because he showed how a black hole can actually radiate. Okay? But then Hawking introduced a second problem, which is called the information paradox. So this fact that a black hole radiates actually leads to a very disturbing consequence that people today are still fighting about. Okay? People meaning my colleagues, not people on the street, but people. Okay? So what's the information paradox? So imagine you find yourself a black hole, and you throw something into a black hole, something that carries information. Yeah? So, for example, a US president. So a US president has some information because he carries something, a small number of bits in his head. So when you throw this into a black hole, what happens next? So it gets absorbed by the black hole. And then the black hole evaporates and emits this Hawking radiation. Okay? And so all of this information that was captured by the president somehow is lost in this evaporation process. And what's even worse, if you take another president and throw him into a black hole, this president might carry more information. Okay? But the amount of radiation that the black hole emits is actually universal. Only depends on the mass of the heads of these two things, and let's say they're the same. Okay? So then the Hawking evaporation that is given off by this black hole is the same, but what went into the black hole was different. So somehow information got lost. Okay? So that might not be a big deal to you, but to a physicist, this is a crisis moment. Okay? Losing information is just not something you're allowed to do in quantum mechanics. Quantum mechanics has a rule that says that any information that goes into a process has to equal the amount of information that goes out of the process. Or you can reverse it, that what went out, if I reverse time, the thing has to look fine. That it has to equal, just there's a balance of information between ingoing and outgoing. Okay? We use a fancy word for this called unitarity. Okay? So in physics, we're not allowed to violate this. This is quantum mechanics 101. Okay? Okay, so what's going on? Is information really lost in the evaporation of a black hole? So at the moment, we don't know. Hawking thought yes. In fact, he made a famous bet. If you squint, you can read this bet. This is a bet between Stephen Hawking, this is his fingerprint, Kip Thorne, who won the Nobel Prize last year, and John Preskill. And so Stephen Hawking and Kip Thorne said yes. Okay, everything they know about black holes and Hawking evaporation means that entropy is lost, and who gives a damn about quantum mechanics? Okay, and John Preskill said, I give a damn about quantum mechanics, and this should not happen. Okay, and so they had a bet about this, but in fact, a few years ago, Stephen Hawking conceded this bet. He said, actually, I'm now convinced that black holes can't destroy information, and Kip Thorne hasn't conceded, and in fact, I don't understand why Hawking conceded, in fact, but okay. So this is actually still an open problem. This question, do black holes preserve or destroy information, is something we as physicists don't have an answer to. Okay? But it's radical. If we accept that black holes destroy information, it means we have to rewrite the laws of quantum mechanics. That's what you have to do. And so quantum mechanics could not be a complete theory, and we would have to find something new. And the reason most physicists think that this cannot possibly be true, because they know how hard it is to do this. Yeah? And in fact, because usually when you try to violate information laws in quantum mechanics, even just a little bit, it's a disaster. So it's like this thing about you can't be a little bit pregnant. In quantum mechanics, you can't violate information even just a little bit. It's all or nothing. So, okay. So this is in fact everything I wanted to say about black holes, why they're puzzling, and why Stephen has done more than anybody, I would say, about first resolving one puzzle and creating another. Okay. Are there any questions about this part? Yeah.
Could you wait one moment before you have the microphone, that people in the back can hear your question?
Yeah, thank you.
Yes.
How do you measure the surface area of a black hole? I thought they could only be observed indirectly.
Very good. Yeah, so this is a theoretical argument. In fact, we have never observed a black hole directly. Okay? So, well, everything I told you here is a thought experiment. Okay? You could also ask me, have I seen this cup of coffee thrown into a black hole? Where did it? Yeah. This is all a thought experiment, and then we just use our theoretical understanding of the laws of nature to derive the consequences of that thought experiment. Yeah. And for example, just if you solve Einstein equations, you will find a round object that has a certain surface that's with an area, and that's the surface of no return, the event horizon. So we define the surface area that way by just what our equation tells us where the surface bounding area of the black hole is. Okay. So for this type of theoretical thought experiment, I don't need to measure it, because my equations do tell me, what's the bounding area of a black hole.
Okay, thank you.
Anything else? Yeah.
Back. There you go. Okay. Thanks.
Okay, you showed that the temperature of a black hole goes as 1 over the mass of a black hole, which means that when I throw something in a black hole, its temperature would decrease. So when I throw energy in a black hole, its temperature would decrease.
Yes.
That seems a little counterintuitive. Is there a physical explanation for that?
Yes. So these pairs of particles that I showed you were created on the outside of the black hole. The one that falls into the black hole actually has negative mass and negative energy. Yeah? And so that negative mass object will actually subtract mass from the mass of the black hole. So it is a feature of quantum mechanics. You can throw something in and lose it, and make the object that absorbs it decrease in size. Yeah. But that's how the energy balance works. So you could also ask, there's energy that's emitted, of course it has to shrink, because energy has to be balanced as seen from the outside.
Instead of it like shrinking by absorbing negative mass, could it be the opposite according to like Einstein's theory, the E equals mc squared, which means like mass can be converted into energy? Is it possible that the mass or the information lost could be just converted into a form of energy?
There were too many things in that question for me to... Maybe we can keep that for later. Yeah. I didn't understand the question. So.
So you said it wasn't quite understood why the entropy scales with area?
Yes. Yeah, nobody knows.
For some reason I thought it was quite obvious. I kind of forgot why, though.
So it's something that follows directly from Hawking's derivation, okay? But it's puzzling because usually entropy, every other system in nature that we have studied, entropy scales as volume. Yeah? If I take a box of gas and I double the size of the box, I will double the entropy of the system. Okay? That's how we usually expect entropies to behave. For the black hole, Hawking tells us this is not the case. The entire information content of the black hole is somehow encoded into the surface area. This is actually, people think this is deep. This is a deep principle called holography. And in fact, Eric is leading a big research effort in the Netherlands to understand precisely that holographic aspect of gravity. That somehow in gravity, when you talk about gravity, yeah, everything else works as volume. But somehow when you talk about gravity, everything is encoded in areas. It's like a hologram where you can have three-dimensional information encoded on a two-dimensional surface. Okay.
Right, I remembered my actual question. So since everything in the universe basically interacts with the actual event horizon of the black hole,
yes,
wouldn't it make sense that the entropy is dependent on the area of it and not the volume?
Well, all I'm saying is that it's just not what we're used to from any other object in nature that we've ever looked at. So if it makes sense to you, then kudos to you. But all of us are very intrigued by the fact that somehow, usually because entropy is also a measure of information. And so usually we think that the information is captured by every little atom that's spread out through space. Okay, and there's information carried by these little atoms. And so we think we can spread that information over the volume of space. But somehow when we talk about gravity, it doesn't. There's a more efficient way of representing the information that's just on the boundary, yeah, on this area. Okay, so let me go on actually because I do have 3 parts. We can come back to these questions later. Okay, so then in the second part, which will be shorter, I want to talk about the Big Bang. And in fact, that's my own area of expertise. So it actually turns out that the Big Bang itself, or the universe as a whole, has certain features that are very similar to black holes. And so a lot of the insights that Stephen Hawking had on the physics of black holes actually carries over to the physics of the universe. Okay, and I will show you this quite explicitly. But let me first remind you a little bit about the basics of the Big Bang. Okay, so you all know that the universe is expanding, because you're a sophisticated audience. And because the universe is expanding, we know that at early times it was denser and hotter. Everything was compressed. So the universe was hot and dense. In fact, at very early times, it was so hot and so dense that stable atoms couldn't exist. If you tried to make a stable atom, it would take a very short amount of time, and it will be hit by another atom and be ripped apart. Okay? So the universe at that time was just a very violent soup of particles like the electron and the nuclei, like a hydrogen nucleus, and light. Okay? So this soup of particles. And during that period, light couldn't get very far. It's like a very dense fog that you can't see through because there's so many interactions between the light and the particles of this so-called plasma, this violent soup. But then the universe is expanding, and as the universe expands, it cools. Okay? And when the universe cools, at some critical moment, which was roughly 400,000 years after the Big Bang, it cooled just enough for the first stable atoms to form. Okay? And when the first stable atoms formed and the universe became neutral, that's the moment when light could propagate freely. When this fog that I was describing kind of lifted, and you can, for the first time, see light propagating through the entire universe. Okay? And this light is very famous. We call this the cosmic microwave background. This is light that should be all around us. It's an afterglow of the Big Bang. It's heat given off from the Big Bang. And it's, in fact, right now, as we're speaking, this light is coming and going through our bodies. Okay? And so this light should still be around today. We should be able to see this afterglow of the Big Bang. And in fact, more than 50 years ago, Penzias and Wilson, kind of by accident, discovered this light. So they had the big radio antenna. This is this radio antenna. This radio antenna was collecting radio waves. And they found a signal which was completely uniform across the sky. So when they scanned their telescope across the sky and measured these radio waves, the intensity of those radio waves were the same everywhere. So they found an image like this. Okay, pretty boring. You could translate the intensity of the light that they found into a temperature. And so this was a temperature of 2.7 degrees Kelvin. So 2.7 above absolute zero. So still damn cold. So minus 207 degrees Celsius. But it was completely featureless. And the fact that it was completely featureless told you also that it was not some signal that was coming from our own galaxy. It or for some distant galaxy, but it was something that had to be created by the universe itself, because it's the same everywhere. Okay? However, when people then looked more carefully, so starting in the 1990s, people built very sophisticated satellites to measure this radiation with higher and higher sensitivity. And so then they started seeing deviations from this uniform temperature. Okay? So when they looked in one direction of the sky, they saw a little bit higher temperature than average, and when they looked in another direction of the sky, they saw a little bit less than average. But very tiny fluctuations. This is 1 part in 10,000. So you have this average temperature of 2.7 degrees and a few hundred millikelvin deviations around this very uniform temperature. Okay? In fact, also something stunning happened in this data set. If you look very closely, you'll see two initials, an S and an H. And so, in fact, as I'm going to be describing to you, the origin of these fluctuations are very intimately tied to Hawking radiation, and somehow Hawking, put his signature on it. It's unfortunately, if you take this data set, it's less visible anymore because the resolution got better. So you have to use this old data set to see this. Okay, so but what are we seeing here actually? Okay, so these are fluctuations across the sky. And it might look like just random noise. So hot and cold, randomly sprinkled across the sky. But they're anything but random. If you analyze these fluctuations statistically, they're actually very systematic and very correlated. So somehow a fluctuation here knows about a fluctuation far away. So there are correlations amongst these hot and cold spots across very large distances. Okay? So we would like to understand why. Yeah? Why isn't this just random noise, but why there's somehow a hot spot here knows about the presence of a cold spot at some distance. Okay? So I don't have time to go into this in detail, but it turns out that you can explain this structure of the map that we have seen if you postulate that the very early universe went through a period of very rapid expansion, when the space was expanding faster than the speed of light. Okay? And just for a short amount of time, you started at, say, 10 to the minus 34 seconds, and you let the universe explode through a very, I don't like the word explosion for a universe, actually, so let the universe expand, okay, in a very short amount of time, just this fraction of a second. A region of space that's smaller than the size of an atomic nucleus becomes the size of an orange, okay? I actually wanted to change this image because, so that's actually size of a I want to change this image because maybe you don't know what the size of a nucleus is. Does anybody know size of a nucleus? So size of a nucleus is, what is it, 10 to the minus 14 meters or something like that? What I wanted to illustrate here is that you take a small region of space and you blow it up by a factor of 10 to the 26, and that gives you an orange, okay? So, for example, you could take the Earth and blow it up to the size of maybe the Milky Way or something. That must be bigger than that. Just this factor of 10 to the 26. It's an enormous increase of space. But in just a very short amount of time, it's a very violent process called inflation. Okay? So what Hawking and many others realized is that if you now again think about empty space during that period of very rapid expansion, and as we learned in quantum mechanics, empty space is not really empty. It has these virtual particles that are popping in and out of existence. And so you create this pair of particles, a dark blue and a light blue one, and then this pair of particles gets stretched apart by the expansion of space, faster than the speed of light. Okay? And so this rapid expansion also creates real particles, not just virtual. It makes these two particles real because they get separated by such a large distance that they can't meet each other anymore to annihilate. Okay? So you have these small fluctuations. In the absence of this expansion, they would just annihilate a moment later. But because of this rapid expansion, they can't meet anymore. Okay? And so you create real particles, just like Hawking radiation. In the case of Hawking radiation, you had this pair of particles. One of them fell into the black hole. The other one got real. Here you have a pair of particles, and they just get separated by the expansion of space. But otherwise, it's the same process. So we could call it, people don't, but we could call it Hawking radiation if we wanted to. And then these particles here actually create fluctuations in the density of the early universe. And it's those fluctuations in the density that create fluctuations in the temperature of this early light that we saw from the Big Bang. Okay? So this process that kind of goes back to Hawking explains that from everything that we see in the universe is explained by this. Okay? So there were small quantum fluctuations that get stretched apart. Those small quantum fluctuations became the fluctuations in the cosmic microwave sky. Those small fluctuations then grow over time into clumpy objects. This is dark matter object clumps here, and then form galaxies and stars. Okay? So all the galaxies and stars, and then humans are just end products of whatever happens around a random star in some random galaxy. But the whole playing field of stars, galaxies, and planets is created through this process. Okay. So for me, we're still trying to figure out whether this story is complete and absolutely true. But if we do, then this is one of the biggest scientific discoveries of all time. Okay. I find it a beautiful story. Okay. Are there any questions about that part?
Me again.
Hey.
So you said that about 380,000 years after the Big Bang is when the first light started floating around the universe.
Yes.
But even nowadays, in our sun, there's a very high density and very hot plasma.
Yes.
And photons from the core still, over very, very long time,
Yes.
escape the sun.
Yes.
So could it be that even older photons from before the 380,000 years were bouncing around the plasma for quite a long time, and then at 380,000 years escaped from that plasma?
Oh, that's a nice question. Okay, so first of all, let me give you a fact. Okay, so the density inside of the sun was not as high as the density of the early universe. Nevertheless, it actually takes 40,000 years. If you create a photon at the center of the sun, it takes 40,000 years until to get to the surface of the sun, and then it takes 8 minutes to get to us. Okay? So that was happened for the sun. Now imagine this, but it's a very similar process. Actually, this process is like an inside-out sun. Okay? The early universe was a plasma, just like the inside of the sun. And when the universe became transparent, that's just like the surface of the sun, and we see the radiation coming from that surface. It's a very nice picture. But it takes much, much longer because it's much denser for a photon to... A photon can travel much shorter distance in the early universe than it can travel in the center of the sun. Okay, so that's why. Okay. Okay. All right, we can come back to this stuff. So the question is, how much time do I have left to talk about time? Yeah, I was thinking 5. Okay, so Hawking also at the end of, throughout his life had very speculative ideas. So I want to make sure that I'm clear. The first 2 parts that I talked about, are fantastic stuff, but they're as close to scientific fact as we can come. They're very solid theoretical ideas, okay? Especially the first part about black holes and even the second part here. This part here now is much more speculative, and not all physicists and theoreticians agree that this is how the universe began, okay? So, just to be clear. But since it's late and we're ready to speculate about what might have happened at the very, very early times, at the beginning, in fact, okay? And in fact, Hawking even, called this his greatest work, okay? I'm not sure if I agree, but he thinks this kind of stuff was actually the best thing he ever did. Okay. Okay. So that's one comment. The other comment is that it's very hard to explain. Okay. So I was always of the opinion if you try hard enough, it's possible to explain everything, and if you're given enough time, it's possible to explain everything. This I'm not so sure, because I've asked 6 of my colleagues over the past week, I've talked with Thomas Hertog, in fact, who was mentioned before, Stephen's collaborator, how he would explain. He's an expert on this. Okay, how would he explain this? I asked my postdoc, how would you explain it? I asked a student, how would you explain? Everybody gives you a different explanation. Okay, and all of these explanations involve something, complicated. So, for example, my postdoc would tell me, okay, really, you have to tell them first about the path integral method of Feynman. And then you have to tell them that this path integral only converges when you do a Wick rotation to imaginary time. So it's a Euclidean path integral. And then you tell them that the instanton action is, instanton dominates the saddle point approximation. All gibberish, okay, to you. So I can try to translate these things, but it's hard, and it would take me an hour, okay? So I'm going to give you a sketch in 5 minutes, okay? And if those 5 minutes don't mean anything to you, then it's fine, okay? We can talk about other stuff, but it's 3 slides where I try my best to kind of just give you some cartoons of what this is all about, but it's tough stuff. Even if I try to explain it to a physics colleague, if that physics colleague isn't trained in the kind of stuff that we do, it would be hard to explain, okay? Okay. But I want you to try. This is maybe not a good introduction. I want you to try, to understand this. Okay. Okay. But the big question is, and maybe that should motivate you to try. The big question is, we want to understand, how did the universe begin? How did everything begin? Maybe more modestly, what happened before inflation. So there was this rapid period of expansion, but actually we know that this rapid period of expansion wasn't the beginning of everything, and we might want to ask, what was there before? And what started this expansion. Okay? So this was Hawking's proposal. This proposal came actually very shortly after he realized that these Hawking particles, this Hawking radiation could apply to the universe itself. Just a year later, he suggested something much more bold. Yeah? So far we have talked about the spontaneous creation of particles, individual particles living within the universe. So what Hawking thought is that the laws of quantum mechanics also allow the spontaneous creation of a pair of universes. Yeah? 2 universes. Yeah? A whole universe, everything there is. Okay? So the idea is that you start with nothing. Okay? And by nothing, I mean really nothing. So no space, no time, no nothing, except the laws of physics. Okay? The laws of physics exist. And then from this state of nothing, you can calculate the probability that you will form this pair of universes. Okay? 2 universes, and one of them might be ours. And there might be more of these spontaneous universe creations somewhere else in space. But let's just focus on one. And so what Hawking also showed is that when this universe is formed, it's actually a very special universe, because at the beginning, time and space are really indistinguishable. They're the same. I mean, you have heard that in relativity, time and space, it's a bit unclear. Different observers observe time and space differently. There's really just one thing called space-time. But the idea here is that something much more dramatic was happening at this early moment. Time was literally like space. Okay? And so what's special about space? What's special about space is that space doesn't have to have a boundary. So we are living on the surface of the Earth, and the surface of the Earth does not have a boundary. Okay? So we can define the surface self-contained without specifying what happens at some boundary of space. Okay? So the idea was that time was exactly like that. That at early moments, time was like space, and therefore didn't have to have a boundary, didn't have to have a beginning as such, because it could be curled up into just a circle of space. So the entire universe was just a 4-dimensional ball of space. Okay? And asking what happened before is meaningless. You don't have to say, to ask me what happened before this ball was created, because there was no time. It was all space. Okay? And asking what happened before is the same as asking what's north of the North Pole. Okay? You're sitting on the North Pole. What's north of the North Pole? The South Pole, yeah. But okay. Okay. If there's anybody who has done any physics here, the more technical way of describing it would be say that you're describing time with imaginary numbers, not real numbers. And when you describe time with an imaginary number, it becomes space. Yeah, because of relativity. Okay, that's why this is called imaginary time. Okay. Okay, but something else, the first feature is that you don't have to specify what happened before, because there was no before. It's a self-contained universe that was just created and then just existed. The second amazing feature is that when you started with the state of just space, it will spontaneously evolve into an expanding universe, but not any arbitrary expanding universe, but an expanding universe that's inflating. Okay? It could have done something else, but somehow this ball of just space will then spontaneously grow into a universe that's inflating and not something else. Okay? So this might be an explanation for how inflation started, and Stephen Hawking liked it very much. Okay? So maybe this is a good time to stop.
Well, thank you very much for your very nice presentation. Very lively, very really tried to explain these hard theoretical things. So thank you very much. And there's about to be quite some questions from the audience. So I know somebody here in the front who would. I need a microphone. Just a sec.
There's a question.
It's a question about your first part.
Okay.
Yeah, thank you for the nice talk. So I want to ask a question about the Hawking radiation. So if one particle is created inside the black hole, but another particle is created outside, but the gravity force would still be really strong there. So how can this other particle can escape from the black hole? Because you need a very high initial velocity.
For example, one of the particles that can be created like this is particle of light, the photon. And it will travel at the speed of light. Okay? And so if a particle of light is created just outside of the black hole, it can still escape, because the rule is only that nothing can escape from the black hole traveling at the speed of light. But anything that's created outside that travels very fast can escape, like light. Okay? And in fact, all very energetic particles travel at the speed of light. The mass of a particle only becomes important when they kind of are not so energetic. So a lot of these particles are created very energetically. They travel at nearly the speed of light, and they can escape the black hole. Yeah.
So the edge is very sharp. In some
the edge is very sharp. Yeah. Yeah.
Any more questions from the audience? Oh. In the back? I see a hand.
Small hand.
Same person. I hope you remember your question now.
So, if you get a photon created like this,
Yes.
what would the anti-photon be?
The anti-photon is a photon with negative energy. Yeah.
Okay.
Okay. It's quantum physics. No, it's possible. Yeah.
Any more questions? Or well, I have a small question. Why does you say the anti-particle goes in? Why doesn't the real particle fall in?
Yeah, I asked myself the same question.
I'm sorry.
Yeah, I know. Yeah. Yes. I was trying to hide this. Yeah, exactly, because I was wondering whether somebody would catch me, and then I didn't expect you to be here.
Sorry for
that. But no, because the important point here is that one of the particles had positive energy and the other one had negative energy. And I was always drawing the negative energy one falling into the black hole and the positive energy staying outside, and therefore the black hole loses mass because it's only negative energy that falls in, okay? So actually what defines positive and negative energy is defined by the black hole itself, it turns out. Yeah. So it is quite complicated to explain. So if you take a positive energy particle and you throw it into a black hole, it actually will become a negative energy particle. So the black hole makes this selection effect that it will only pull the negative energy. Well, as soon as the particle comes in, it becomes automatically negative energy and so on. It's related to what we talked about at dinner, where time becomes space, and it's exactly that same thing.
Yeah.
Okay, but you guys weren't at dinner, so.
We had dinner, yeah. Thank you for that. Any more questions? There's a finger at the back. I see a woman.
How do you think this experiment relates to Einstein's theories of relativity in general?
Sorry, which experiment?
Not the experiment, the theory that when positive energy comes into a black hole, then it leaves as a negative energy. How does it relate to the general theories of relativity?
So, okay, maybe just a general comment. I'm not sure if I understand, but let me just say something general and you can say if that works, okay? So the first thing is that in general relativity, black holes are black, yeah? And so black holes don't, and that was the whole issue that Bekenstein and Hawking had, that black holes in general relativity cannot radiate. There's no mechanism for them to radiate, yeah? So it's only when you combine general relativity with quantum mechanics in this special way that you get this radiation effect, and the black hole carries temperature and entropy and so on. So it's not something you could possibly explain in general. It's a fact, if the world had been only described by general relativity, we would not expect black holes to be radiating and disappearing. It's because of quantum mechanics. It's only the fact that a black hole has such strong gravity that makes the quantum mechanics effect significant. Okay? So it's this nice interplay between quantum mechanical fluctuations that happen in empty space and this empty space living very close to a black hole, so that it gets ripped apart into these two types of particles, and one of the particles becomes this radiation that we see. Yeah.
Do you think the black holes have enough strength to achieve 0 degrees Kelvin at the center, for example?
At the center of what?
Of the black hole itself.
I'm not sure what that would mean. So actually, we have as physicists, we have a lot of trouble describing the interior of the black hole anyway. So what we would like to do is, in fact, be able to describe our world just as seen from the outside of a black hole, because you don't want to go into a black hole. And just seen from the outside, the black hole has temperature. And it's a temperature that Hawking calculated. So what happens inside of the black hole, you know, is for you to find out if you jump in, but I can tell you it's various scenarios that will happen to you, but none of them pleasant. But,
Thanks.
Any other questions in the far back? Yeah. Thank you.
So about the information paradox, he believed, he changed his mind that information was conserved, right?
Yes. Actually, I know because he did concede this bet.
Yes. So that gave rise to a firewall, the black hole firewall, I believe.
That came later.
Yeah.
That came later.
Did he come to any insight in that before his death?
Okay, good. Let me say two things, actually. So the reason he changed his mind is because of something called ADS-CFT. It's a work by a brilliant Argentinian physicist, Juan Maldacena. And so what he showed is that he showed an explicit example of this kind of way of describing information just by a theory living on a boundary, like for black holes. And what he showed is that a theory that has gravity can be described completely by a theory without any gravity in a lower dimensional boundary, in a very special space. But now gravity is completely lost. This theory in the boundary has no gravity, and it should just respect the ordinary laws of quantum mechanics, because there's no gravity that could mess up the laws of quantum mechanics. And it's for that reason that Hawking thought that now there's no reason for quantum mechanics not to hold anymore. Yeah, it's because of this kind of very indirect theoretical reasoning that there is now a theory that describes gravitational effects and black holes purely from the point of view of quantum mechanics without any gravity. And the laws of quantum mechanics tell you that information cannot be lost. That's why he changed his mind. Then fast forward a couple of years, okay? People revisited this information paradox in a slightly more sophisticated way. And they were asking themselves basically what happens when my dear friend over there jumps into a black hole, okay? And it's a very puzzling, actually, maybe let's talk about it if we have a minute, okay? So let me ask you this, okay? Imagine you have two people, okay? Her and you, okay? You are sensible, so you decide to stay outside, and she wants to jump in because she wants to know whether there's zero temperature in the black hole for some reason, okay? Okay? So she will jump into the black hole. She will just freely fall into the black hole. From her point of view, time runs normal. Nothing special happens when she crosses the event horizon of the black hole. When she gets in, it becomes a little bit uncomfortable because gravity becomes so strong. that her head will be pulled much, her feet will be pulled much stronger than her head, and she becomes spaghetti and so on. Okay. You look at this whole thing from the outside. Yeah, what do you see? What you see from the outside is her falling in time slowing down because she's flowing, in a very strong gravitational field. And Einstein's theory actually tells you that in a strong gravitational field, clocks go more slowly. Okay? So as she's approaching the black hole, the clock that you're measuring it with becomes slower and slower. And the light that you see from her becomes more and more stretched because the light has to escape from the black hole. So she becomes redder and redder, more and more embarrassed, be so foolish to jump. Okay? And then when she reaches the surface of the black hole, from your point of view, time stands still. And she actually never crosses the horizon of the black hole. Okay? Okay, so but worse than that, okay? Because just before that happens, you actually still saw this very faint radiation, and you can trace that radiation back and ask, it's only very faint and very low energy because it had to escape the black hole. But near the surface of the black hole, what was the energy of this light that was emitted? And you would find that this light is enormously large. It's X-rays, yes, say. So she would you would think that before she even gets into the black hole, she will just be radiated by X-rays and die, okay, before getting into the black hole. So there's already this conflict from these 2 points of view that you will think she will be dying by X-rays, while she will think I will just be spaghettified when I go into the black hole. And the question is which, okay? Those kind of thoughts have been made kind of more sophisticated, let's say, by physicists in the last couple of years. And they're more puzzled than ever what really happens when you reach the surface of a black hole. And you said this buzzword of firewalls, that like maybe we used to think, and up to 3 years ago we thought nothing special happens, you just fall through. And I still think that's the case. But some physicists start thinking that actually something very dramatic will happen before you get into the black hole. There's some surface of very intense radiation that will kill you. I'm not sure what the question was.
That's not resolved yet.
That is not resolved at all.
Okay.
Yeah. Okay.
Thanks.
It's a new version of the information paradox that had made it's even worse than what was going on before.
Any more questions? I have maybe one bit more easier question. Maybe it's easy question. Why since Hawking was so intelligent and such a good scientist, why did he never get the Nobel Prize?
Oh, okay. Yeah, it's a special rule. I think it's a very sensible rule of the Nobel Prize that Nobel Prizes are awarded for kind of things that are experimentally verified. Okay, so the reason we believe black holes have entropy and evaporate and all those kind of nice things that Hawking discovered is because we have confidence in our theories. Okay, but confidence in our theories is not a substitute for experimental confirmation of our theories. So everybody thinks these things are amazing, and if Hawking evaporation, Hawking radiation were seen at any moment in time, he would get a Nobel Prize instantly. Okay, not anymore, but for another rule of the Nobel Prize, but he would have gotten it instantly if there was any just evidence for Hawking radiation. Yeah, very good.
So,
yes.
I'll repeat that answer because nobody can.
Yeah.
To repeat it in the microphone, please.
Oh, sorry. I just have to say that it's the same applied to Einstein. He didn't get his Nobel Prize for the theory of general relativity, which he would love to have, and many people think he should get it, but he got it for the photoelectric effect, which is an experiment, and that's how he got his Nobel Prize. So it was a big struggle also for him to get the Nobel Prize.
Yeah.
But he got it.
Yeah. Thank you very much. If there are no more questions for the audience, from the audience, I would like you all to give a big hand to the speakers again and thank them for the nice presentation. And as a token for our appreciation for you to come here, I have a book for both of you, which is the same book for both of you. It's a book about personal impressions from people in their how they met Einstein and their experiences with Einstein. And these letters and these experiences are bundled in this book. We hope you don't yet have it, so please enjoy reading it. Well, this is the real end of the evening. Thank you very much for coming, and enjoy the rest of the evening without thunderstorms, I hope.